All right, in this example, we want to look at another circular waveguide problem. In this case, we have an airfield X-band, which is 8 to 12 gigahertz. It's a WC94 circular waveguide, which has an inner diameter of 2.383 centimeters. The goal of the problem is to determine the cutoff frequencies for the modes TE11, TM01, and TE21. To find the modes that will propagate through the sky at 10 gigahertz, and finally, to find the guide wavelengths for all the propagating modes at 10 gigahertz. Then we want to find the frequency range within which only the TE11 mode propagates. So, four-part question here. The first thing that we do is we solve for the TE11 mode, and that expression is given for the cutoff frequency of TE11 is 1.841C over 2 pi A. So we look at that, we plug in A for the radius and C for the speed of light since we're in air, and then basically we get 7.38 gigahertz. We repeat the same thing for the TE01 and the TE21 by using the ratio. So here we have 2.4049 over 1.8412. That's approximately 9.64 gigahertz. The TE21 is approximately 12.2 gigahertz. So, you could go back to this original formula, re-plug in C and A, and instead of using the 8.412, you could use the 2.4049 and use this formula 3 times. Sometimes this book author does things in a weird way. He seems to love ratios, so he's basically solved for this one using a ratio problem. So that's how, so if you wanted to reuse this formula over and over again and just change this constant, you could certainly do that. So that's how you get the cutoff for the TM01 and the TM21. So noting 7.38 gigahertz, 9.64, 12.2. So verifying that this is the dominant mode, the TE11, at least of these three. So the next thing that we can do is we can, at 10 gigahertz, figure out which modes will propagate. So if you look, because that was the next question that was asked, what modes will propagate at 10 gigahertz? So at 10 gigahertz, you see that there are 2 of these cutoff frequencies that are below 10 gigahertz. So 10 gigahertz will propagate in the TE11 and the TM01 mode. And then you can see that the TE21 mode has a cutoff of 12.2 gigahertz. So the 10 gigahertz wave will not propagate in that mode because the frequency is below 12.2. So once again, the cutoff frequency cuts off frequencies lower than the frequency of interest, but not higher. Okay, the wavelength in the guide can be found by taking lambda over 1 minus the ratio of the cutoff frequency to the frequency squared under the square root sign. So basically you can do that on your own by determining the value of lambda and then just plugging that in for the desired cutoff frequency. Now the frequency range over which the dominant TE11 mode propagates along the guide can be found by basically taking the difference between the TM01 and the TE11. And so you can see that if you take 9.64 and subtract 7.38, you get 2.26 gigahertz. So also here is the lambda in the guide for the TM01. So basically in this range here, what you want to know is what's like the bandwidth that you can have before you pick up the next mode. And so that's why they're taking the difference between the higher mode and the lower mode to determine if you're above 7.38, below 9.64, you're only propagating the dominant mode. Okay, another example, let's look at an airfield cubical cavity. So this is a resonant cavity um, where A is equal to B is equal to D. So this is a rectangular or a cube. Um, it's a rectangular resonator, but it's a cube because all the dimensions are equal. They're designed to be resonant in the TE101 mode at 10 gigahertz. Um, and the wavelength is lambda equal 3 centimeters. And they have a silver plated surface, so you're given the conductivity, surface conductivity, and you're told that this is a non-magnetic material, so mu is equal to mu naught. And asked to find the quality factor. So this is a resonant cube, and you're given the mode, you're given the frequency. So using the previous expression for the resonant frequency and the fact that the cavity is air-filled, we can basically calculate the dimension A for that. And if we plug in all other relevant information, we get that A is 2.12 centimeters. At 10 gigahertz, the skin depth for silver can be found from the formula from the book for a good conductor. And so the skin depth for silver ends up being 0.642 microns. So we can find the quality factor by taking A over 3 times the skin depth. So the quality factor for the cube is roughly 11,000. A similar problem, this is a Teflon filled cavity. This is also cube. Um, we found earlier that when we had silver plated walls, the quality factor was 11,000. Now what we want to do is look at what happens when we fill that cavity with Teflon and find the total Q for the cavity. This is the complex permittivity for Teflon. So using that, and that A is approximately 2.12 centimeters, and A and B and D are all equal. Basically, once again, we find since the dimensions of the cavity are different. Now, why are the dimensions of the cavity different? Because we're using the same frequency. And so the cavity dimensions, instead of just speed of light, we have the speed of light over square root of mu r epsilon r. And so the formula adjusts a little bit, meaning that we have to resolve for A based on using a phase velocity, not just the speed of light. So when we do that with our desired resonant frequency and mu r equal to 1 for Teflon, basically the cavity is the square root of epsilon prime r times smaller, so 1.48 centimeters. So then when we take that and we plug into the formula, we get the quality factor is 7,684. So you can see that when you put a dielectric into a cavity for the same resonant frequency, the cavity size has to get smaller, and you find that the Q also gets smaller. So then the quality factor due to the dielectric losses is given by taking epsilon prime over epsilon double prime, and out of that we get 3,417. We then find the total Q by basically 1 over Q is 1 over Q dielectric plus 1 over Q conducting losses. And so you have to invert that. It's kind of like resistive losses. So when you use this formula, Q dielectric, Q conductor over Q dielectric plus Q conductor, you get 2,365 for the Q of this cavity. So you can see it gets even lower when you consider the dielectric losses inside the cavity as opposed to a cavity that would be air-filled. Okay, for our final example, let's look at a microwave oven design. In this problem, we have a microwave oven. It's built from WR1150 aluminum rectangular waveguide. Dimensions A and B are given. We now want to set D equal to A. The length of the guide is D. Both ends are closed with aluminum sheets. So when D is equal to A, we want to find the resonant frequencies of the two non-trivial TE MNP and TM MNP modes. that have the lowest resonant frequencies. We then want to redesign the oven by readjusting the length D so that the resonant frequency of the TE101 mode is 1 gigahertz. And then in part B, what are the resonant frequencies of TE102 and TE011? So the resonant frequency Mn and P is given by C over 2, and then the A, B, and D dimensions are given here, and M, N, and P are given here. So if we look at TE101, 102, and 011, then we would be plugging in for M, N, and P with 1, 0, and 1 respectively, and for A, B, and D with the known given parameters. And notice that for the first two modes, the B part goes away because N is 0. So you have 1 over A squared plus 1 over A squared for TE101, and you have 1 over A squared plus 4 over A squared for TE102. And then for TE011, you would have 1 over B squared, 1 over D squared. So for the 101 mode, we get 726 megahertz. For the 102 or the 110, we get 1.15 gigahertz. So similarly, the modes with the lowest resonant frequencies are TM110 and TM210, and we get for the cutoff frequency of TM110, that's equal to 102, and that's 1.15 gigahertz, and 210 can be found to be 1.45 gigahertz. So basically they're just literally plugging in values for M, N, and P for our given A, B, and D in order to find the resonant frequency. And remember, this frequency, I may have said cutoff earlier, this frequency is actually not a cutoff frequency, it's a resonant frequency. It's basically the only frequency at this mode that will resonate in this cavity. Now for the TE101 mode, if we look at the resonant frequency for that, we can basically use the same formula, and what we want to do here is solve for D because we want this to be equal to 10 gigahertz or 10 to the ninth. So, sorry, 1 gigahertz. So if we set that equal to 10 to the ninth and we solve for D, we end up with 17.5 centimeters. Finally, using a D of 17.5 centimeters, the resonant frequencies for TE102 and TE011 are 1.79 and 1.34 gigahertz respectively. Okay, the final thing that we want to look at is to look at a circular cavity design. We want to design a circular cavity that has D equal to 2A so that the TE011 resonates at 10 gigahertz, and we want to determine the Q of the cavity. So for the TE011 mode to be resonant at 10 gigahertz, you have to have lambda 011 equal to C over F011 equal to the following formula, okay, where A is the cavity dimension. And so we can basically solve for the cavity dimension and get A of 1.98 centimeters. So that's kind of similar to the 2.12 centimeters for the cubical resonator that we found in example D2. But the interesting thing is, if we now assume the same kind of silver-plated walls, so we've kind of got the same dimension, we're going to assume the same silver-plated walls, we're going to assume air, and we're going to do a calculation of the Q of this cylindrical cavity. Basically, you find out after substituting for the relevant terms, you find out that your Q is 30,792. So you might remember that our Q before was 11,000. So just by going to a circular cavity for a similar frequency and for similar material, we have a Q that's 3 times higher. So this has to do with the volume to surface ratio of a cylinder compared to a cube.